Hello, everyone. Welcome to this session, and welcome to Reinforce, the inaugural security conference at AWS. I'm sure you are excited about this conference, and so am I. So let me start with a quick story around how we came about with this talk. Back in February, Stephen Tallamy here, who is going to co-present with me from Synamedia, they were doing a migration program around Kubernetes, and they're moving over some of their Kubernetes clusters to Amazon EKS. And there were some security controls they were looking to implement, and they were looking for guidance from us. And with the solutions architecture team, I sort of specialize into containers and Kubernetes security. So we spent some time looking at some of the solutions and came up with a proof of concept for Stephen and the team. And Reinforce was about to be announced. So I talked to Stephen about this idea. How about we share our learning so that our customers, the wider customers, learn and benefit from our experience. So this is the talk. We'll go deep dive, level 400, and we'll have exciting demos which you can sort of learn, get more insights about Amazon EKS and Kubernetes security in general. And we'll try and keep this session fun and interesting. So towards the end of the session, I'll be sharing some interesting demo around how we implemented the controls. So stick around till the end. And this video will be on YouTube later as well, so feel free to refer it then. So this is SDD411, Security Deep Dive, architecting security and governance through policy guardrails in Amazon EKS. My name is Pavan Mistry. I'm a specialist security solutions architect with AWS, and I've been with AWS for around nearly 5 years now in various security roles. And I'm delighted to be joined by Stephen Tallamy from Synamedia. Stephen is a principal cloud architect and will be sharing his story around Kubernetes migration and security and governance. So before we go ahead, let's look at the agenda and what we are going to cover. I'll start with a quick Amazon EKS overview. It's going to be real quick. This is level 400, so we won't spend too much time, set the basics. And what I'm really excited about is sharing with you the data plane security and the authentication around Amazon EKS. So after that, Stephen will come on stage and go through the governance and security for Kubernetes and the migration program he led. And Stephen brings a great amount of experience running live Kubernetes clusters and Amazon EKS as well. So that'd be a great section of the talk. Finally, we'll cover policy guardrails on Amazon EKS using an open source tool called Open Policy Agent. How many of you here have heard about Open Policy Agent? Excellent, quite a few. Great. So looking forward to this. Before we go ahead, there are some container and Kubernetes security sessions and workshops at the event, so feel free to attend those and make a note of those in agenda. So to help us understand, get an understanding of the audience today, how many of you are using Kubernetes today? Great. So that's about 3/4 or more of the audience. And how many of you are using it in production? Great. So half of the audience. So excellent. You're in the right place. So let's begin with a quick Amazon EKS overview. So within AWS, containers are first-class citizens, and we have various options for customers to run their containers on AWS. For the orchestration tools, we launched ECS, and it was generally available in April 2015. ECS is a sort of container orchestration service. Elastic container service, and it provides sort of a managed control plane, and it provides our customers a deep integration with AWS services. So and ECS sort of offers a couple of launch types as well, where you'd run your containers. The first one is EC2, where you manage your own instances where your containers run. And the second is Fargate, where if you do not want the heavy lifting around managing your instances, you would give that responsibility to us, and all you would worry about is your task definitions and making sure your containers are running the right controls, which it has been really popular as well. Now, in the open source world, there are several options on orchestrating your containers, and Kubernetes being the most popular one, as most of you know. So with a recent sort of last CNCF, or Cloud Native Computing Foundation survey, we found that 51% of the customers run Kubernetes on AWS. Or 51% of Kubernetes users actually run on AWS, and that's one of the reasons why we created Elastic Kubernetes Service. What Kubernetes Service offers our customers is a data plane running on EC2 nodes or EC2 instances, and we are soon sort of working on bringing out AWS Fargate for EKS as well. So the reference to number 32 on the slide is a reference to a GitHub issue, which we'll come to later. Great. So Kubernetes consists of a control plane and a data plane. And the control plane consists of a scheduler, a controller, and an etcd distributed key value store, and the API server with which the data plane interacts with, and customers can interact with remotely as well using the endpoint. And the data plane is made up of nodes or EC2 instances, and within each node runs a kubelet, or which is the primary node agent, and a kube proxy, which is the Kubernetes network proxy. So the workloads or the containers which customers create actually run within those nodes, and the nodes can be from one to many, as in customers can configure their cluster according to their requirements, and Kubernetes control plane does all the orchestration, management, and scheduling around it. So Amazon EKS provides a managed control plane, which means that customers only need to manage their data plane that consists of nodes and containers that run your applications. AWS manages the control plane components that we saw in the previous slide. I mean, one of the key features of Amazon EKS is its Kubernetes certified confirmant. And what that means is it runs upstream Kubernetes, and that when customers do that, the applications running on Amazon EKS are fully compatible with applications running on any standard Kubernetes environment. So one of the benefits, or one of the obvious benefits that comes with a managed control plane, especially with AWS, is compliance. So this means that customers who are running workloads or have requirements around these specific sort of compliance programs do not need to worry about their managed control plane or getting their managed control plane compliant, because today they already get these compliance programs with their Amazon EKS managed control plane. This also means that customers own a part of the shared responsibility model. So for the security and compliance of Amazon EKS, it consists of the data plane security and the container security that the workloads are running on. So this can be sort of separated into data plane security lifecycle and container security lifecycle. And this is how I like to view it. We will focus on the data plane security lifecycle. due to the scope of this presentation, and there are several other container security presentations which you can deep dive into in the conference, which will help you learn more about container security lifecycle as well. So let's talk about the data plane security, and this is the section I'm really interested in going through. I strongly believe that to build a useful threat model, the underlying system needs to be well understood. And to build a threat model and secure the data plane, customers need to understand what's running within it to get the value out of it. So let's understand this through a quick demo. So in this demo, we'll log on to an active node, which is part of the Amazon EKS cluster, and look at the kubelet configuration. We'll use kubectl, which is a CLI client, to interact with nodes, and we'll observe that the binaries which are run within the node. We'll also look into sort of getting a shell and see what runs underlying the node. So you'll get a good idea of what happens within your node in a real-time basis. So this demo provides some insights into the components involved on the data plane and how they operate. So let's jump right in. Okay. So this is actually what we'll go through. Okay, so we're logged on to right here. We're logged on to a node, and we'll take a look at the kubelet process running on the node. So there are several parameters which are running here. First, we note the container runtime, which is Docker. We'll note the networking parameters as well. We note that the nodes are labeled using EKS control, which is how we build this cluster. Authentication and authorization is done through Webhook. This is something we'll come back. And the PKI configs. Now, we'll run a watch on the Docker runtime. So what we see is that Docker is running as a process, as a runtime, and containerd and containerd shim are run to manage the containers and how they are brought up and killed. In the next window, I'm running exec-snoop BPF, which is a trace running on the BPF, using a trace running on all the exec calls happening in the kernel for these 4 binaries. So now what we'll try and do in the other window is use kubectl, which is the client you'd use, to bring up a small container and get a shell into it. So this will show really what happens and goes on when you create a container or a pod within the node. So what we see really is the shim calls runc, and runc starts the container and logs the container, and then you'll see that the new containers are brought up, and you get a shell as well. So the shell is a process within Docker, and you follow the same process for bringing up that process with runc. When we exit out of the container, the interesting thing happens where the 2 processes are deleted, and runc again is called and deletes and kills all the containers. So hopefully this provided you with some really real-time sort of insights into what really goes on in bringing up a container or a pod within your node. So what we learned is that kubelet is the main, sort of owns the config for the node, and the container runtime does all the heavy lifting around managing the containers within the node. To help build a threat model for the data plane, so you may question sort of who's responsible for these components. So you saw containerd shim, or runc. Who really owns these open source projects, and how is the security managed? That's a very valid question. So for containerd, it's a graduated CNCF, or Cloud Native Computing Foundation project, and it goes through a security review, and the report is published on the GitHub repository. For runc, interestingly, it's an open container initiative project, and it has a different management platform. What I would recommend is you take a look at this recent talk given at KubeCon, Kubernetes conference in Barcelona, which explains and deep dives into the security reviews. Now, having mentioned Run C, you might be aware of this vulnerability which came out in February, and we published a security bulletin around it. So there have been a few Kubernetes and container security issues lately, which we have published and communicated to our customers. We also published deep dive analysis. In this case, for Run C, we had a blog, which was a really deep dive analysis of the actual vulnerability. And this is something you can fold into your threat model as well. And Kubernetes has a security support cycle which you need to be aware of. So Amazon EKS aligns with that support cycle, and we provide guidance on what that upgrade cycle looks like. We wrote a blog recently and have recently upgraded or provided support for 1.13, which, as this slide shows, was announced. So last week we announced 1.13, which some of you may have noticed. So at a single point, we support 3 versions and provide guidance on how to upgrade the managed control plane and the worker nodes as well. So the key takeaway from the data plane security lifecycle is have these controls baked in. Make sure before going into production, have the test, update, and upgrade program and document it. So let's move on to authentication in the context of building your threat model. So you might have noticed in the demo, we used the kube control to bring up the container, and we also looked at the kubelet parameters for authentication. So this is very interesting because the way we authenticate is using the webhook mechanism in Kubernetes. So to use the identity from AWS and not create an additional user or role within Kubernetes cluster, Amazon EKS uses a bearer token webhook feature in Kubernetes, which we noted earlier in the config. And through AWS I Authenticator, this is done through AWS I Authenticator. So it's an open source project which I've linked here, and it runs on a node as a client and on the masters as a server. So when whether a request is coming from a kubelet or a kube control or an application which you've created within your cluster, and the request is made using that token, which is generated by AWS IAM and sent to the API server, and the API server then looks at the request and sends it again to AWS IAM for authentication. And then the authorized request, authenticated request, is sent to Kubernetes API server for authorization through Kubernetes RBAC, so role-based access control. And once this is completed, a response is then sent to the client. So let's look at a quick demo around this. And in this demo, what we'll see is really look at the token in depth, what it consists of, and also from a remote host or a rogue host on the internet, so using some parameters, take a look at how authentication works. So we'll enlist the API endpoints and a particular endpoint in this demo. Right. So here we look at the endpoint, or generate, take a look at the API endpoint and the token, which is a base 64 encoded token. We decode that token, and what we find is something familiar. So we have an STS get caller identity call, and it's making a request using the known SIGV4 signature. So you see the parameters, the signed headers, and the signature, which is the same format goes for AWS I Authenticator as well. So when you decode the request coming out from the authenticator, it has the same STS get caller identity. So here we are just logging into a remote host. It can be any host on the internet. It's a Ubuntu host, and what we are establishing here is it doesn't have any AWS credentials or kubelet or any Kubernetes parameters within it. And what we are doing is a curl or an HTTP request with a header which has the cluster name within it, and we are using a token which we generate using the AWS IAM Authenticator. So when we use this request and point it to the API server endpoint, we are authenticated against the API. So we are successfully authenticated, and we get a list of all the API endpoints. In this case, we are listing, validating and mutating webhooks. So that's something we'll come back to later. And when the request expires, we won't be able to authenticate, and there's a failed or unauthorized output. So hopefully this gave you a good understanding around how authentication works within Amazon EKS and what's the role of AWS IAM Authenticator. So we'll take a sort of broader look into IAM for EKS, but before we do that, I'd like to point out that when using EC2 instances as nodes for the Kubernetes EKS cluster, customers benefit from other AWS security services as well, some of which are listed here. So you can use the features which most of these services have, like VPC endpoints. And I wrote a blog last year around using Secrets Manager, for example, to connect with your nodes and use secrets from AWS Secrets Manager. And you can do so for some of the other services and leverage the value they offer. So when a cluster is created within Amazon EKS, a role is assigned to the nodes, and this role is inherited by the pods created within the nodes as well. So we are working on a roadmap feature to enable sort of fine-grained EKS IAM roles for pods, which is a request from quite a few of our customers. And speaking of our roadmap, the containers team, or the product roadmap, is available publicly on GitHub, and that's one of the unique things that the containers team have done. The number 32, which I referred to in my previous slide, is the reference to a work in progress issue for Fargate for EKS. And we constantly communicate to our customers on the new features that we ship. And these are some of the relevant features around security and storage that our customers really liked. So the second input around your threat model for the data plane security is you do to review the cluster IAM and limit the resource access, and use the container roadmap. So I would strongly advise you to open issues and communicate directly with our product team and ask for feature requests, or at least take a look at those and monitor them. So quickly want to touch upon container security lifecycle. So CIS, these are some of the journeys that the customers would take, not in this particular fashion, but one of the key features that was announced with 1.13 is pod security policies, and this is something I'm really excited about. So take a look at the blog, which was written recently by my colleague Michael Hausenblas, and I want to leave you with a couple of messages around the best practice to how you'd secure your Amazon EKS data plane and container security. And I'd like to hand it over to Stephen for the next session. So thank you.
Thank you, Pavan. Can I just get a show of hands that you can hear me okay from this mic? Yes? Good. Okay, good. Excellent. So hi, everyone. I'm Stephen Tallamy. I work for a company called Synamedia, who you may not have ever heard of. So just as a kind of background of who Synamedia are, we make video solutions for service providers all the way around the world. And we're deployed globally, so you may recognize some TV providers on that thing. But I'm not going to talk about TV, and I'm not going to talk about any of that stuff. I'm going to talk about EKS and how we're using it. And we're using it... We're using it really to underpin a number of our different products and solutions. So we have our foundation platform, which is there for our broadcast systems. And then we have the Infinite platform, which is hosted in Amazon. We actually run it as a service and manage it ourselves. And then we have things in terms of video security, video processing, and cloud DVR. So again, we take security very seriously because it's underpinning the revenue of our customers. So I just wanted to give you a kind of an idea of our deployment architecture and how we're actually going about deploying services both on-prem and in the cloud, because some of our customers have requirements for on-prem, some are happy to be in the cloud. And our sort of dilemma here was really, how do we get our applications to be built at speed with agility whilst being able to support these two different worlds, the cloud world and an on-prem world. And so what we did was we made sure that all of our app teams write to the Kubernetes API. So when they're deploying, that is the API that they're interacting with. And then we have a platform team who are there to glue that Kubernetes layer down onto the underlying platforms. And so when it comes to on-premise, we're using OpenShift as our container platform. And until recently, we've been using OpenShift also in Amazon, but have been migrating to EKS. And that's what I'm going to talk to you a little bit more about today. But before I do that, I'm just going to give you a kind of an idea, just so you can kind of compare and contrast the difference between what it looks like when you're rolling your own Kubernetes in Amazon versus EKS. So this is a typical deployment architecture we would have. So to the left-hand side, we might have some load balancers that's bringing in traffic from the outside. It's distributing to various nodes, so EC2 instances that are acting as the Kubernetes workers. And those Kubernetes workers are then being allocated pods and containers by the control plane. So in this case, because we are rolling our own Kubernetes, we have to bring our own control plane. So you can see we're bringing our masters. We need a load balancer in front of those for high availability and scaling. And then we have to have another number of other things that we have to stand up. So because OpenShift is run using Ansible, we need a deployer that can SSH into these machines and provision them. We need a Yum repo so we can install all the RPMs and our own Docker registry for all of the containers. So there's quite a bit of infrastructure that we're having to manage and secure the lifecycle of. And we've had quite a lot of success in doing this. It's actually been quite successful. As Pavan said, we've rolled out many Kubernetes, very large Kubernetes clusters, both on-prem and in the cloud. We've gone through all the experience of upgrading those things and the pains of doing so, keeping track with the latest versions of Kubernetes. And that's given us a nice consistent deployment pattern for on-prem and AWS. But there is a real challenge there with keeping up to date with the upgrades. When you're rolling your own Kubernetes cluster, keeping on top of the new release every 6 months. It might not seem like much, but it's when you're in a larger organization, that can be really difficult. Also, because we're provisioning our own infrastructure, so we're standing up these EC2 instances ourselves, we sort of miss out on a few nice features that you might come to expect, like auto-scaling groups or other things. Now, these are things for sure we could do, but there's a lot of extra work we're having to do ourselves on top of, an open source Kubernetes distribution. And also the overhead of managing our own operating system. So we bring our own CentOS operating system. We have to secure it, manage it, and make sure it works with that particular version of OpenShift. So there's quite a lot of work there for us. So if we compare and contrast kind of how that looks with OpenShift to EKS, you'll notice immediately that quite a lot of the pain has been taken away from us. The control plane is now managed using EKS. We've then got CloudFormation templates coming in instead of using Ansible. So we don't need to stand that infrastructure up. We can use the AMI provided with EKS. So again, that's something we don't need to manage a lifecycle of. And again, we can also make use of the ECR, the Elastic Container Registry. So again, that's a nice secured registry. We don't need to worry about it. There's a whole bunch of things there that Amazon are taking care of for us in the security management of our system. I just wanted to share a few kind of things that we've had to experience as we've moved from rolling our own, particularly because we've been rolling an OpenShift. So OpenShift takes a slightly opinionated view to how it deploys Kubernetes, which is a good thing because at least it's sort of controlled and they can test the life cycle of it. But they bring a few extra services in, one of which is the OpenShift router, which provides you with the ability to sort of do host or path mapping into a single ingress point, and then that can distribute to containers within the Kubernetes cluster. We had to move that over to an open source option, which is the ingress controller. So that's a standard thing that Kubernetes does out of the box. And there's an Nginx one out there, which we decided to use. There's also one that integrates with ALBs, but for our workloads, it just wasn't quite the right fit. We moved from using Docker registries to ECR, which again is great, a great thing for us. There were some changes that we had to do in our CI/CD workflow to make sure that we could authenticate correctly with ECR so that when we're pushing our containers into it, everything worked as it should do. But there are a few things that we've had to bring ourselves, and now we're now responsible for the lifecycle, the security lifecycle of. Those include the Kubernetes dashboard, so there isn't one of those available with EKS at this moment in time. Cluster autoscaler, metric server, so there's a bunch of things there that we're having to manage the lifecycle of. But we're working with Amazon to sort of request features so that they start to take care of those components as well for us. Now, we do deployments on-prem, and we do deployments in AWS. So I just wanted to kind of share a little bit of how our hybrid of those things work. So for those of you not familiar with Private Link, this is just a very quick recap of how that works. So typically, left-hand side of the diagram, you've got a provider network, a VPC that's being the provider of a service. So it might have a bunch of EC2 instances running and a network load balancer in front of it. And it exposes those through an endpoint service to allow other VPCs to then connect into it. And so we've got then a client VPC here with a private subnet. It has an endpoint which has an ENI inside of its VPC. So it looks to its point of view as if it's inside its VPC, and that allows then access through to that NLB. And we've been making quite good use of this technology because it simplifies a number of things. It also secures things for us. So this is kind of going back to the architecture I showed on the previous slide, sort of overlaying the two of them. So again, as we had before, we've got the Kubernetes workers there running. And what we do is we point an NLB at those Kubernetes workers, typically to the ingress controller. That then allows us to expose an endpoint service into a remote VPC. Now, in our case, it's not a remote VPC of a customer. Typically, it's one we're managing because we're wanting to connect to an on-prem network. And so we came up with this concept of a proxy VPC. It's something we work with Amazon on. And effectively, what it does is it creates a remote VPC that's carved out with a CIDR range that's within the on-prem network. So typically, we find we might be provisioning our VPCs with fairly wide IP ranges. And so typically, we might end up clashing with something on-prem. So what we do is we create this proxy VPC that's got a much smaller number of IP addresses. It doesn't need many because they're mostly these endpoints. And then what we do is we take our on-prem network, we connect them up typically through AWS Direct Connect. And then when something on-prem, so if it's maybe a Kubernetes cluster on-prem wanting to connect in, or clients, they come in through the Direct Connect, they hit the endpoint, and then that resolves to services inside of EKS. We can do the same thing in reverse as well. So if some service that's over in our on-prem Kubernetes needs to be accessed from EKS, we can come through an endpoint, pointing at an NLB, and then that comes through to the nodes that are on-prem. So again, this is giving us a really nice deployment architecture for sort of having a hybrid between the two, but with very clear security boundaries between what's on-prem and what's in the cloud. So I just wanted to give you a little bit of some practical experience that we've had in sort of governance around deployment of Kubernetes. And these are real examples of stuff that we've had to work through, so I'm not making this stuff up. So I just wanted to put a quote up there. You may be familiar with this one. It comes from Spider-Man. With great power comes great responsibility. And this is very true for Kubernetes. Kubernetes is a very, very powerful framework. It has a lot of parts to it, and they're a lot of power that you're giving to your engineers because they can deploy applications very, very rapidly. But there's a lot of responsibility then on the security side to make sure silly things don't happen. So I'm going to give you three powers that you have, three examples of powers that you might have when you deploy with Kubernetes, and some of the responsibilities of those. So the first one of these deployment powers that you have is the marketplace of containers, right? There's loads and loads and loads of open source containers that you can go and grab from Docker Hub. There might be a Helm chart that you can go and grab that will automatically provision that into your cluster. So you can spin your cluster, your EKS cluster up, load one of these charts, and off you go. You've got containers up and running. And this is a lot of power, right? It means that it's very, very easy for people to manage these open source technologies, etcd or whatever it is that you want to do. So there's a lot of power there. But the responsibility then is to make sure that you're auditing what is going on here, right? Those Helm charts, they could have been attacked by somebody. Somebody could have come in and done something bad, right? Or made a malicious YAML file and distributed it in some way. And if you're not auditing that, perhaps that YAML is actually opening an ELB through the node ports that you can provision inside of Kubernetes to an attacker to then go and compromise your system. Or they might be pointing at a container, and that container itself has been compromised. And there are a number of examples and incidences out there in terms of this kind of issue. So there are a number of places where an attacker can come in, and if you're not auditing through this life cycle of things, you're just getting people going out and they go, yep, I'll just run that thing in production. What could go wrong? You can see some serious vulnerability there. There's some great tools that we've been using to help us along with this. If you're not familiar with Quay, Quay is great because it scans a lot of these open source Docker containers. So you can see here some of the different versions of the container and whether they have any security issues. So this is great in terms of ongoing monitoring of things. And you can run this yourself, or you can run the public version. And also, we make great use of ECR for this boat. So we actually, our container lifecycle always brings in containers. It verifies they're okay. We put them through a number of security checks, and then we push them to ECR. And then we only deploy our containers from our ECR. So we know that we have controlled the lifecycle of those containers. So the second great power that you get, and this is a great Amazon power, but when combined with Kubernetes, again, a really good power. So I'm just actually showing, this is actually a non-Kubernetes picture. It's just a very traditional picture of an EC2 kind of world, where you might have had a couple of VMs, types of VMs, some front ends, some back ends, and they might have an IAM role associated with them that gave them access to a number of services. So, you know, front end buckets or back end buckets, maybe a Kinesis data stream for pushing your log files and so on. So this is kind of like how things might have looked if you're running VMs. They are kind of host-centric roles. Now, if you start to do this in Kubernetes, well, then you have those roles. Well, how do you manage those roles? You have to attach them to an EC2 instance in this case. And then, well, I then now need a role that actually can give me access to any of these things, because Kubernetes could schedule any of these things that are now pods, they're containers rather than VMs, anywhere in my cluster. Well, this isn't particularly great because now my back-end pod has access to the UI, my front-end pod has access to billing buckets. It's not a great situation, right? So you need to go and solve this as you move towards a sort of containerized workflow. Now, sort of a typical way to go and solve this might be to create credentials. So for each of your IAM roles, create users, create credentials, mount those credentials into the containers using a Kubernetes secret. So then each one of these things now can have their own role, and they can have a credential for it. And actually, this is slightly better because now the log agent only has access to the Kinesis data streams. The front ends don't have access to those things. So there's better separation. But now we've got a challenge, an overhead of managing the life cycle of those keys. You know, we need to cycle those keys, manage them. So there's a lot of headache in doing that. And we've been doing this for a while. It's actually the way we manage it, and it's not great. We end up having to do a lot of automation ourselves. But there are a few solutions out there, and a couple that we looked at that Amazon sort of pointed us to was Kube2IAM and Quay. They're quite popular. Each of them kind of take their own approach to providing an IAM mapping to a container. But each of them have their own drawbacks. And so, as Pavan mentioned earlier on the roadmap, there are some features coming in EKS that will actually do that. And that's what we're waiting for, because we think if it's integrated inside of Amazon, then it'll be great. And the way they're going about doing that is they're going to use service accounts, which is something you can associate with a pod. And that will then use an OpenID Connect token to then use the assume role with web identity mechanism. So it's a great kind of all built into the way in which Amazon will work. So I think this is a really good way to solve this problem that you have, the responsibility you take in terms of managing access to from Kubernetes into your other services. And the last of the powers that I kind of wanted to walk you through here, and again, this is another pure example. This is something that we experienced ourselves. So if you're not familiar with Kubernetes, I think quite a few people were so, but if you're not, effectively, when you want to gain access to containers that are running and scheduled inside of Kubernetes, you can use these things called services. And it's an abstract concept that then will distribute load around those containers. And when you first use a service, you'll quite often make that available just internally inside the cluster, so pods within the cluster can talk to each other. But if you want to then expose your service to the outside world, you might then use a service type load balancer. And if you've got this all wired up correctly, and obviously EKS does this, but you can do this with other Kubernetes ones, then what will happen is by specifying type load balancer, it's automatically going to provision you an ELB. It's going to open up node ports, and node port is so a random port number on every node in the cluster, and then it's going to wire up that ELB to those node ports and allow traffic in. So this is great. It's a great power because it makes it very easy for me to automate all of that infrastructure. And by the way, this also can work with NLBs as well as ELBs in some of the newer versions. But the responsibility that you get with this power is that you've now got places where people can make really bad mistakes. So an example of a bad mistake that you could make, so with the way in which a service works in terms of finding the pods that it's going to do, it does it based on pod labels. So each of these labels pods will have various labels associated with them, and the service does a selector to them. So in this case, we had a very generic selector. This is going to pick up anything that happened to have the label type Node.js. My backend could be written in Node.js, my front end could be written in Node.js, and somebody decides they're going to put those labels on. And suddenly you're exposing to what you thought was just your front-end pods, you're also 1 in 4 are going to go to a back-end pod when people access it through the ELB. What a great thing to happen. The alternative would be perhaps somebody comes along, and this one definitely did happen to us, they just didn't really understand what they were doing with service type load balancer. And perhaps that's because they were using a Kubernetes cluster that wasn't wired into the Amazon services. So maybe it was an on-prem cluster where maybe this had no meaning or no effect. Right, but they were using a service type load balancer for their backend service, and suddenly we had exposed to the internet some backend services through an ELB. Not a particularly great situation, got on top of it pretty quickly, of course. But again, you've got some issues here because you've got that power, but you've got the responsibility of providing some governance, and you can give guidelines, but these things can happen in production. It's very easy for someone to just go in and type these commands and off you go. You've got this. So even if you're auditing this through a CI/CD pipeline that's testing and making sure, that doesn't stop someone in production from using kubectl to go and achieve the same problem. And so there are a few solutions to this problem, and actually this is one of the problems we, along with the container management stuff that we presented to Amazon. And I think Open Policy Agent really has a great possibility here for controlling this, because you can use it to write rules and manage what sorts of services you can use, and some guidance around how that gets implemented. And so even in production, you can start to prevent these types of issues. So I'd like to pass back to Pavan, who's going to walk through actually a little quick demo of the of OPA.
Excellent, great, thank you very much. So that's a great message from Stephen around, with great power comes great responsibility, especially when running something so complex and so powerful as Kubernetes. So if you're a CISO or a security manager or a portfolio owner of an infrastructure like this, to operate at scale, you'd need something like a policy guardrail, something that can protect you in a cluster of developers or teams who are free to do what they want or create different resources within the Kubernetes cluster. So we needed that to implement the security controls that Stephen and the team brought to us. And we looked at a few solutions and built a proof of concept using Open Policy Agent. So Open Policy Agent is an incubating project within CNCF. It's a cloud-native computing foundation. CNCF have different stages around the different projects, and Open Policy Agent is one of those projects. So let's take a look at it. To sort of really understand what Open Policy Agent OPA offers is, we need to understand admission controllers within Kubernetes first. And from the EKS, from sort of Amazon EKS point of view and the authentication demo, you may remember that we accessed a couple of APIs. In this case, sort of admission controller API, which led us to look at the validating and the webhook configurations. So what is an admission controller? So the admission controller is like a intercepting code when a HTTP request is authenticated and authorized. It goes through another filter, which is these admission webhooks. There are two main types, mutating and validating webhooks. They intercept the request, and before the Kubernetes API server receives those requests and puts the makes a decision around sort of runtime and sort of persists within the etcd key value distributed store, admission controller is sort of looks at those and inspects the request. So that's an additional layer of control which Kubernetes provides. So OPA, and how does it fit into this? So OPA leverages this feature within Kubernetes, and it's not limited to Kubernetes. I mean, there are several implementations that you should go ahead and look at the GitHub repository. But OPA gives a language to your authorization policies. So it helps you with policy enforcement, and it's decoupled. The policy enforcement is decoupled from policy decision making. So what it eventually does and provides is it provides a desired state security for your workloads. So it introduces a dynamic sort of authorization prior to Kubernetes resources entering runtime. So this model sort of lends really well to some of the challenges that Stephen described earlier. So let's take a look at the demo. And in this demo, we'll take a look at the OPA sort of running as validating webhook configuration, and take a look at the Rego policy, which is the policy which really implements or enforces the construct that you require, and also use or restrict the policy to use images not from, or restrict it from Docker, but use it from ECR. So this is a requirement that Stephen and the team came up with in terms of we do not want our dev teams to pull images from Docker or Docker Hub. We have restricted image lifecycle, and we want containers to be brought in from a particular registry, which was ECR. So this is what we'll look at. So here we'll take a quick look at OPA running within the cluster. We'll have a couple of pods running, and we'll take a deeper look into the validating webhook configuration and see how OPA operates within that construct. So here we see it operates within the validating webhook configuration and not mutating one. We'll also look at the Rego policy, which tells us that deny pod creation if the registry is outside of the whitelisted ones which we have highlighted. So the two registries which are here are the ones which are allowed. So we also look at the pod definitions. One tells us that the image is coming from Docker Hub, Nginx, and the other one is from the ECR, the Elastic Container Registry. So when we try and run the public repository with Nginx, it rejects it using the validating webhook. And when we try the private repository, it successfully creates the Nginx container. So what that tells us is through this policy language, OPA enables Kubernetes environments to be controlled, leveraging the admission sort of webhook feature or admission controller feature, and the possibilities are endless. So you can take a look at IAM or other policies around it, and if you're looking at operating OPA at scale, then we have the founders of OPA who have created Styra.com, and we have Bill, the CEO of Styra, who is here with us, and you can have a look at how you can sort of manage these policies and have these policies baked into your clusters. So these are a couple of screenshots which show container registry and container-based security policies within the Styra console, and also ingress and how you put policies around the ingress. So these are the two sort of rule-based engines which you can sort of leverage through the console or the managed commercial offering. Styra in the process of becoming an AWS partner. Speaking of partners, within the container ecosystem of AWS, we have a rich partner ecosystem. We have partners like Aquasec and Allside and Twistlock with their variety of tools and tooling which can sort of satisfy your specific use case. Allside has Allside Advisor, which I recently blogged about this week, and last week, and Sysdig has Falco, which does deep dive sort of runtime monitoring. Aquasec has a KubeBench CIS benchmark inspector. So you can use variety of these tools and provide sort of those controls and build those controls into your Kubernetes clusters. Here are some of the resources. I'd like to point the security book written by Liz Rice from Aquasec and Michael Hausenblas, who is now a developer advocate at AWS, and a couple of blogs, the Allside Advisor blog and the Secrets Manager blog as well. Some of the YouTube videos, which are really insightful, so I'd definitely recommend go ahead and take a look. So to leave you with our learnings from this experience, there are two main things. Clearly understand the relationship, the boundaries with the shared responsibility model, and build a threat model around your Kubernetes cluster, especially the data plane and the container security life cycles. And as Stephen said, with great power comes great responsibility. So make sure that you have these controls baked in with operating at scale, and make sure your containers and the Kubernetes environment is secure. So I'd like to thank Stephen again for presenting with me, and thank you again for attending. Before you leave, one more thing. Please complete the survey. Your survey and the feedback is really important to us. It makes us better at what we do, and feel free to provide feedback. So thank you very much again for attending.